project manager has to perform the staffing and personnel planning during the various stages of software development. It is very important to find the relationship between the people and effort during the project development. Many programmers and people think that if we are behind the schedule, we can add more programmers and we can perform the project in time without any problems. But unfortunately, adding people late in the project often has destructive effect on the project because there is a complexity with communication with various team members. So Putnam suggested a model. This is the Putnam-Norden Ralph curve, which provides an indication of the relationship between effort applied and delivery time for the software project. There is a minimum value in the curve at T0 that indicates the least cost for the delivery. As we move left of T0, the curve rises non-linearly, and there is an impossible region which says that this project cannot be finished within that impossible region till T-min. T-min is the minimum time required. Putnam analyzed a large number of projects and derived the expression that L is equal to Ck k power 1 by 3 into Td power 4 by 3, where Ck is the state of technology constant that reflects the various factors that affect the productivity of the programmer. K is the effort expended in the graph region in the Putnam graph. L is the size of the program code in terms of thousands of lines of code. Td is the time to develop the software. This is the original Putnam resource allocation model curve. Norden of IBM in 1958 analyzed many R&D projects and observed that number of personnel required during any project development is not a constant value. Later, Ralph in 1970s suggested a model of efforts required with time for the various range of hardware development projects. The figure shows the persons required on y-axis and the time of the development of the hardware projects on x-axis. Later, Putnam observed that this curve designed by Ralph is exactly similar with the cost and effort required with the software subsystem development. This is the Ralph curve. He specified by two parameters. The size of the program is the function of K and Td, where K is the total area under the curve. It is directly proportional to the effort required. And Td is the time at which the curve reaches its maximum. Ralph curve says that very small number of engineers are needed at the beginning of a project to carry out planning and specification. As the project progresses, more detailed work is required so that number of engineers slowly increases and reaches a peak. And Putnam observed that the time at which Ralph curve reaches its maximum value corresponds to system testing and product release. After system testing, the number of project staff falls, reduces till the product installation and delivery. In the relief curve, it is observed that approximately 40% of the area is on the left and 60% is to the right of the TD, the maximum effort taken. Around 150 projects were studied by Norden and subsequently by Putnam, and apparently both researchers observed the same tendency for the manpower curve to rise, peak, and then exponentially tail off as a function of time. Now, Norden-Rayleigh equation represents manpower measured in person per unit time as a function of time. It is usually expressed in person year per year. The Rayleigh curve is modeled by the differential equation m of t is equal to dy by dt equal to 2K t e power minus at square, where dy by dt is the manpower utilization rate per unit time, t is the elapsed time, a is the manpower that affects the shape of the curve, and k is the area under the curve in the interval 0 to infinity. Integrating the equation 1 on interval time 0 to t, we can obtain y of t is equal to k into 1 minus e power minus at square, where y of t is the cumulative manpower used up to time t. Here y of 0 is the initial value 0. There at the beginning time manpower value is 0. Then y of infinity is k. The cumulative manpower is null at the start of the project and grows monotonically towards the total effort k, which is the area under the curve. It can be seen from the figure that the parameter a, which has the dimension of 1 by time square, plays an important role in the determination of peak manpower. The larger the value of a, earlier the peak time occurs and steeper is the person profile. By deriving the manpower function relative to time and finding the zero value of this derivative, the relationship between the peak time Td and A can be found to be d square y by dt square equal to 2ke power minus at square into 1 minus at square equal to 0. Therefore, Td square is equal to 1 by 2a, where Td denotes the time where maximum effort rate occurs. Thus, the point Td on the time scale should correspond very closely to the total project development time. If we substitute Td for T in this equation, you can see that the estimate for the development time E is equal to y of t equal to k into 1 minus e power minus of Td square divided by 2 Td square equal to k into 1 minus e power minus 0.5. So we can write it like this: at time t equal to Td, peak manning m of Td is obtained by denoting m of 0 is equal to k divided by k divided by Td into square root of e, where k is the total project cost per effort in person years, Td is the delivery time in years, M0 is the number of persons employed at the peak time, and E is the value 2.71828. So the average rate of software team building up is equal to M0 by T. Now let us see one problem. A software development project is planned to cost 95 man-year in a period of 1 year and 9 months. Calculate the peak manning and average rate of software team buildup. Now in the solution, software development project is planned to cost 95 man-year, so that it is directly given that the effort software development cost K is equal to 95 man-year. Now peak development time, the time is given as 1 year and 9 months. When we write it in years, the value TD is equal to 1.75 years. We have the formula for peak manning. M0 is equal to K divided by TD square root of E. Substituting the value of K, TD and square root of E, we get the value 32.94, which is approximately 33%. So the average rate of software team buildup is equal to M0 by TD. We are substituting the value of M0 as 33 and TD as the peak development time 1.75 is equal to 18.8% per year, or when we convert it into months, it becomes 1.56% per month.